right, so we're starting off with the first thing on the syllabus, which is states of matter. Right, and this is something that we are already aware of, so we're just going to go through fast with this part. All right, so the first thing that we're going to look at is your kinetic theory of matter. All right, so the kinetic theory of matter tells us kinetic we know comes from moving, right? And then so it's basically it's a theory that tells us how particles or matter moves, right? So the first thing that we note is that matter is made up of tiny particles that are in constant motion because because of the energy that they contain. All right, so all objects on Earth have matter, right? And these are small particles that are just moving random motion, right? Then we know that there's force of attraction and repulsion between the particles, right? So we have attractive forces and repulsive forces between these particles that makes up the objects. So the particles can be atoms, molecules, or ions, right? And we're going to look at those as we go along, right? All right, so the amount of kinetic energy held is determined by the temperature and the state of matter. Right, so the energy that these particles have would be dependent on what state of matter it is, so solid, liquid, or gas, or its temperature that it's experienced. And remember that if it change the temperature to a point, then it's going to change the state. All right, so both are correlated. All right, particles that make up matter can be atoms, molecules, and ions. We know that. And then an atom, definition for an atom is the smallest particle that can be broken down by chemical means. Right, so any chemical changes that happen to an object, the smallest that it can be broken down into is known as the atom. Right, molecule is a particle that's containing two or more atoms. The atoms can be the same or different. So molecules contain two or more atoms, which can be the same atoms or different atoms, just like oxygen molecule, hydrogen molecule, nitrogen. And then we know an ion is atoms or group of ions, or atoms, sorry, with either a positive or a negative charge, right? And we're going to look at those as time progresses. So we know in liquid and gases, the particles and the constant random motion and collision with each other. The kinetic particle theory says that particles in our constant motion, right? So we already went through that. So the particles in kinetic theory, they are in random motion. So how do we prove that particles are in random motion? We use we use these three phenomena that we are going to look at. So diffusion, osmosis, and Brownian motion. So these three things, or three concepts, actually explain to us that particles are always moving, right? So we look at diffusion. So we know diffusion is the movement of particles from where it's high to where it's low, right? So and we know examples of diffusion, right? So can we get some examples of diffusion? Anyone giving in?
When potassium permanganate dissolves in a solution.
So potassium permanganate dissolving in water. Yes, so that's one. All right, any other? Any common ones that we experience in a daily life?
The spray of perfume in a room.
Spraying perfume in a room. Okay, diffusion of gases through air, drink mix in water, right? So all these actually tells us about particles that are moving, right? So if we spray the perfume in the room, we notice that at the point where it's sprayed, that's the area that it's high concentrated with the particles, right? And over a period of time, those particles will spread out throughout the room, right? Till it's actually evenly distributed, all right? So that's the phenomena of diffusion. All right, so we know diffusion in gases is faster than in liquids, all right? And why do you think that's the case, right? Because it is the particles in gas move faster than in liquids because the gases have more spaces between the particles so they can move freely, so they can move faster than the ones in liquids. There is little or no diffusions in solids. The reason for that is because of how compact the particles are within the solid, right? So that's the reason why the particles in solids don't or mine or will exhibit minor diffusion. All right, so we talked about the permanganate in water. So we notice the permanganate is at the bottom of the water or the beaker. All right, so over a period of time, even without stirring it, the particles will start to move in the liquid until all the permanganate particles are evenly throughout the mixture, right? All right, so with the demonstration with gases, this is an experiment that I think most students will do, the diffusion of gases where we use concentrated hydrochloric acid as well as ammonia, right? So if we have both in a tube at two different ends, right, each particles of each gas will move. And when those two particles of each gases mix, they actually produce what is ammonium chloride. And ammonium chloride is actually visible to the eye as a white cloud, right? So at C there, that's where the gas will be produced. Now, if you notice that the gas is produced at closer to where it's hydrochloric acid. Anyone knows why the gas is produced closer to hydrochloric acid and not in the center or closer to ammonia?
Did it did it use particles of ammonia move faster than that of hydrogen chloride?
All right, so ammonia moves faster than hydrogen chloride. But why is that the case? Anyone knows why?
Because it's denser than the other one.
Because which one is denser?
The hydrochloride is denser than the
All right,
other one.
so the hydrochloric acid is denser than the ammonia. All right, because if we look at the mass number of each element, so hydrogen we know has a mass of 1, and chlorine has a mass of 35.5. Right, so that is basically 36.5 for hydrochloric acid in its mass. If we look at ammonia, nitrogen has a mass of 14, hydrogen is 1 and it's 3, so it's 3. So 3 plus 14 is 17. So we notice there is a big difference between the mass of ammonia, which is 17, and the mass of hydrochloric acid, which is 37.5, 36.5, sorry, right? So because the HCl is heavier, it's going to move slower than the NH3, which is lighter. So that's why it's closer to the HCl than to the ammonia, right? All right, so that's what we just talked about. All right, so because of that difference in the mass, we can find the rate of diffusion, right? So the speed of diffusion is the fastest in gases, as followed by liquids, and then slowly through solids, right? At higher temperature, the particles have higher kinetic energy, hence move faster and diffuse at a faster rate, right? So giving particles increase in temperature will cause their energy to be increased. So that means that they're going to actually move faster. The rate of diffusion also depends on the relative molecular masses of the particles, which we just highlighted for ammonia and hydrochloric acid. The rate of diffusion in a gas depends on its density, right? And if you do physics, then we know that density is mass over volume, right? And because it's the same container, then the the volume is the same for the gases, but the masses are different. So the ammonia mass is higher, is lighter, sorry, than the HCl, right? And then the heavier particles will diffuse at a slower rate than the lighter ones, which we just explained, right? So in that case, the rate of the first one over the rate of the second one is given by their, so the M2 and M1 would be the masses of each gas. All right, so the mass of the HCl and the mass of the Na3 in this case, we'll divide those and find the square root to get us the rate of diffusion. All right, and we get a number without a unit, so 1.47 would be the rate of diffusion of the gas that will be produced in this experiment. All right, and we know osmosis now is where it involves the water molecules. All right, so movement of water molecules from high to low through a semi-permeable membrane. All right, so we have to have a membrane or a barrier in which the water particles will move from one side to the next, right? So it's a form of diffusion, but the membrane part is very important, and it also only works with water or liquid, right? So can we go with some examples for osmosis?
Salt as a preservative.
Could you repeat that, please?
Salt as a preservative.
Salt as a preservative. All right, do you want to explain how that exhibits osmosis?
Mm, well, I think the salt draws out the water from the cells of the food items, and when they are dehydrated, it doesn't serve as a haven for microorganisms anymore.
Okay, great. All right, so the salt will actually has less water concentration than the food particles. So the water in the food particle move from that high to the low where the salt is. So basically, salt is pulling the water from the food particle, so we don't have any bacterial growth. All right, any other example? One more. Any more example of osmosis? A potato strip absorbing water and increasing in size. Right, and I think that's a lab that you guys would normally do, especially in bio, right? So just put in potato strips in different concentration of salt water, right? So if it has more salt than water, then that means the water from your potato will go into the salt water. If it has less salt than water in your concentration, then the water from the salt water will go into the potato. All right, cucumber as well. All right, so those are examples, and we notice these, they have a barrier between the water concentration inside the cucumber or the potato and the water concentration outside. All right, so there is a barrier there. All right, and then we know Brownian motion is the final one that depicts the motion of particles, where Brownian motion is a constant and irregular motion of particles, right? So this is where it shows that particles move in a haphazard random motion, especially in air, right? And we can experience this with smoke. So when you notice smoke in the air, it moves in random motion. Or if you have a gap, small gap that light passes through in a dark room, especially in a dark room, you see the air particles moving in a haphazard manner. So that shows us Brownian motion, right? So at that diagram there, notice all particles just move in random motion. That blue line is identifying one of the particles moving, and you notice it just moves in a very random motion. All right, so let's look at a question here. All right, so we just did some of these, so we can skip some. All right, and we just answered A, B, and C. All right, let's look at D. Using the kinetic theory of matter, explain the formation of ammonium chloride ring. All right, so why did we, if we soak a partner with HCl and one with NH3, why do we have a gas that is produced at the white ring? Anyone wants to answer that one? Anyone?
The ring is the point at which the particles diffuse from the ammonia and the hydrogen chloride meet. So it's the reaction between the diffused particles of both substances.
All right, but according to the kinetic theory, which one of those points will cause the particles to move basically? So which one of the points from the theory will cause us to have the movement so we can get that white ring?
Well, matter is composed of particles, and particles are in constant motion.
All right, great. All right, so particles, each matter is made up of particles and they're always in random motion. So that's the reason why we have the white ring that is produced. All right, so that's the first one for matter. All right, let's move on to the next one. All right, before we move on, any questions or anything you'd like to go over? All right, so now we're going to look at the three states of matter. All right, so we know we have three states of matter: solid, liquid, and gases. All right, so let's go and fill out this table here. So based on the volume, we know that solids have fixed volume. Fixed volume means that it doesn't change its volume based on its container that it's in, right? So what about liquids?
Fixed.
It's fixed, okay? And we know gases.
Varies.
Varies depending on its container, right? And the shape of solids,
Fixed.
fixed. And fixed there means that the shape does not change regardless of where it is.
Yeah.
Liquids
Varies.
varies.
Takes the shape of its container.
Exactly. So liquids will take the shape of the container, and gases
Takes the shape of its
also
container.
takes the shape of the container. All right, compressibility. So how well is it able to be compressed? Solids,
Not easily compressed.
not easily compressed. Liquids,
It can be compressed, I guess.
yeah, can be slightly, yes. And then gases,
Easily
Compressible.
compressed.
easily compressed. All right, so we're going to look at compressibility for a minute. All right, so what makes solids hard to compress but gases very easy to compress?
The particles in solids are closer together, while the particles in gases are farther apart,
All right,
causing them to be easy to move around and also.
okay. All right, so we know that solids particles, as we can see in this diagram here, they have a very small space in between them, right? So in this case, we have particles don't have enough space. So compressing means that we're reducing the spaces between the particles. But solids already have reduced spacing, so it's hard to get um, the particles go any further closer together. But if we look at the gases, right, we notice there are a lot of spaces between these particles, so we can easily reduce those spacing by compressing it, right? So that's the difference and why solids are hard to compress while the gases are easier to compress. All right, and we know about the forces of attraction between the particles. So for the solids, the forces of attraction between particles are strong, so that the movement is limited to vibration, right? So we know that particles vibrate in a solid because they have no minimal space to move about with, so they only can just vibrate around a fixed point. The force of attraction for liquids are weaker, right? So that's the reason why they can have more space in between their particles. So the particles can slip over each other just like in water. And for gases, we have force of attraction is very small. So the particles are free to move wherever they want, right? All right, so we just did this. All right, so we're looking at the different changes of state. All right, so let's go through and should remember all. So let's go from solid to liquid. So solid to liquid, what change is that? Melting?
Sublimation. Oh,
No, not sublimate.
liquid.
Yes. All right, so solid to
Oh,
liquid, melting. All right, liquid to gas,
boiling or
boiling or
evaporation.
evaporation. All right, and then liquid to solid,
Freezing.
freezing, right? Freezing. All right, and then gas, solid to gas,
Sublimation.
sublimation, and then gas to liquid,
Deposition.
condensation. All right, so the thing now is what makes each of these changes happen, right? What's the main factor that would cause us, if we have a solid, to actually change to a liquid, or if we have a liquid to change to a solid? So adding heat, so heat. Right? So heat is important in all these changes. All right. So all right. So let's continue. All right. So we identify all the changes of state, and required is heat. All right. So let's see the first one. All right. So melting. So we know melting is from solid to liquid. And in this case, if we're dependent on heat or temperature, then we have to apply heat. So we need to apply heat to a solid in order for it to actually change to or melt to a liquid, right? And adding heat is actually increasing the temperature. And increasing the temperature, all it does is to give the particles enough energy so they can break away from each other, right? So breaking away from each other would cause the particles now to have space in between so they can actually change from the solid state to the liquid state, right? And then we look at freezing. So freezing, we know, is a reverse of melting. And in this case now, we're removing heat. So with melting, we added heat. With freezing, we're removing heat. So the freezer in your fridge, all it does is to remove heat from the substance, so it can actually change from being a liquid to a solid, right? So removing the heat, all it does is to remove the energy from the particles, so the particles can now sit closely to each other and reduce the space in between them. Right? And then we look at boiling from liquid to gas. So in this case, we're adding heat because we now need more space in between our liquids to become a gas. All right, and evaporation is the same process as boiling, but there's a difference between evaporation and boiling. Anyone knows that difference?
Evaporation, the vapors escape from the top, while boiling, it takes place throughout the whole liquid.
Great. All right, so evaporation takes place from the surface of your liquid, while boiling takes place from in the entire or in the middle of the liquid. All right, and then we have condensation, which is from gas to liquid. And in this case, we're removing heat from a gas so they can actually come closer together now to become a liquid. And then we have sublimation, which changes directly from solid to a gas, right, without going into the liquid phase. Right, an example of sublimation is iodine crystals, they sublime, and ammonium chloride and naphthalene, right? So these are important examples, and dry ice as well. So these are important examples of substances that right? So these are important examples of substances that sublimes, right? So it's important that you know, especially ammonium chloride, it's normally in multiple choice questions, right? So ammonium chloride, dry ice, iodine crystals, and naphthalene. Very good examples, right? All right, so let's look now at our heating curve. So the heating curve actually gives us what happens when temperature changes and over a period of time, right? So we notice that we start from point A, right? So we start from point A here with a solid object, right? So let's use ice, right? So at point A we have ice at 0 degrees. So right here is 0 degrees, right? And then as time changes, we're going to add heat to that ice, right? So at this point here, this is the temperature at which it's going to melt, right? So the ice now melts, right? So through A and B, between A and B, we have a mixture of solid and liquid, right? And then when at B now, we have the liquid phase, so we have water at B, right? And then we continue to heat that liquid. So we're heating it until it reaches D, and at point D there, that's where we start getting our liquid starts to boil and we have evaporation of the gas, right? So we have solid, liquid, and at this point here, E to F, we're changing over to being a gas, right? So that is our heating curve for any substance. It doesn't have to be water, right? It can be any substance that we will heat to make it go through all three states of matter. All right, so that's additional reading on what happened between the change of states, which we already went through before. All right. All right, and then because we have heating curve, we also have cooling curve, where this is where we reduce the temperature. So we start from a high temperature and reduce the temperature gradually. So we have the same change of state. All right. So we start off at point A with a gas. It's cooling, so we're cooling the gas. So cooling a gas will cause it to condense, right? So we get a liquid. So a liquid is formed at point C. Then that liquid now going to D. Now still temperature is reducing. So it now going to freeze that liquid to become a solid, which is from E to F. All right, so those are our change of states and the process used for changing our states. All right, so we did the first three rows. All right, so let's look at diffusion. So summary of solids. So solids and diffusion. What would we put here?
Don't diffuse.
What's that?
Diffuse? I don't diffuse. I don't think so.
Don't are very. Yeah, so we'll give it. Liquids. Diffusion in liquids.
Diffuse at us. Well, I don't
Yeah.
know what to say.
So it
Slower
diffuse, but it's slow.
than, yeah.
All right, so you can say slower than gases. And then for gas, it would be
Rapidly.
rapid
Yes,
or
rapid.
fast. Great. All right, the effect of heat on solids. What effect does heat have on solids?
Causes it to turn to liquid or to gas. Change state
All right,
to
so
liquid or gas.
exactly. So it's going to melt and it also causes it to expand slightly as well. Right? And then for liquid, what heat effect does heat have on liquids?
Yeah.
So vaporization. So it also causes a slight expansion of liquids, right? And you know it's going to boil or evaporate. And then for gas, still have expansion, much more than solid and liquids, right? It causes a great pressure as well, right? So that's important to know that when you heat any solid, liquid, or gas, you will have an expansion of the particles or the material that you're heating, right? So the greatest expansion will happen in a gas, right? Because it's just going to get it the particles further away from each other, right? All right, so let's go through these questions, which we just a recap of what we just did. All right, so state whether heat energy is absorbed or released in each of the following processes. Melting, So is it absorbed or released?
Absorb.
Observed.
Absorbed. All right, boiling,
Release.
Release.
released. All right, so let's go back to melt.
Absorbed.
Let's go back to melting, right? So what we're saying is if heat, so if you're applying heat, which is it will absorb it to change for melting, or it would release it from the substance for melting. So with melting, remember melting is from solid to liquid, right? So if we need to change from solid to liquid, we have to apply heat to it,
Absorb heat.
right? So therefore it will absorb.
Absorb.
All right, so melting would
Boiling is
be absorb, boiling,
Absorb.
uh,
Absorb as well.
absorb, freezing,
Release.
Release.
it would release, right? And then condensation,
Release.
release as well. All right. All right, state whether the speed of the particles increase or decrease during the following processes. Melting, does the speed of particles increase or decrease?
Increase.
Increase.
Increase, great, because we have more spacing. Condensation,
Decrease.
decreases, because we're moving from a gas to a liquid, yes. And boiling,
Increases.
increase. And freezing,
Decrease.
Decreases.
decreasing. All right, the information below gives the melting point and boiling point of 4 substances. For each substance, whether it is a solid, a liquid, or a gas at room temperature and pressure. So we know room temperature is 27 degrees, right? So we're going to use 27 degrees. So let's go. So W, substance W, what state will it be at 27 degrees? What state would it be?
Solid. This.
Gas.
Solid?
Oh, that's negative. Gas.
Yeah, so both negative. Gas? Everyone agree with that?
Yeah.
Yes, sir.
Yes, so it will be a gas at 27 degrees. All right, X,
Liquid.
liquid, right? Great. The Y,
Solid.
solid, great, because it hasn't reached its melting point as yet. And then the last one, Z,
Liquid also.
it's
Liquid. Yeah.
a liquid. All right, and in which substance are the particles furthest apart at negative 60 degrees?
Mm, X.
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 X,
X.
There.
yes. Someone said no?
Yeah, I said yes. X.
Oh, okay, yes. So X is the answer. All right, so the last one for the states of matter. No, we just did that one. So we're going to move on to pure and impure substances. All right, so first, before we look at pure and impure substances, we have to define some specific terms. All right, so an element. So an elements are substances containing only one type of atoms. All right, compounds are substances containing two or more different types of atoms chemically bonded together. Substance is a matter which has a specific composition and specific properties, which are physical properties or chemical properties. So physical properties are the ones that do not generally depend on the amount of substance present. So just like melting point, electrical conductivity, doesn't matter how much of the substance you have, water will still boil at 100 degrees, right? So it doesn't matter if it has a small amount or a large amount. And chemical properties describes how elements and compounds react with each other. Example in chemical reactions. All right, so a mixture. So we know a mixture is an impure substance that contains two or more different compounds. It's made up of two or more substances not chemically bonded together, which can be easily separated. Right? So with mixtures, we can separate them easily because they are not chemically bonded together. All right, and we know for mixtures, we have two types of mixtures, which are
homogeneous and heterogeneous.
so we have homogeneous and heterogeneous. Right? And for heterogeneous mixtures, we have what is our colloids or suspensions, which we're going to look at. Right?
Mhm.
And then homologous, we have our solutions. All right, so if we look at pure and impure, so we compare boiling points of pure and impure substances. So pure substances have short melting points and boiling points. If a substance is impure, the impurities will affect its melting point. The boiling point of liquid is increased by adding other substances. So if a liquid is impure, yes, is there a question? All right. So if a liquid is impure, then its boiling point will actually be increased from what it was. So if water has impurities, it's going to actually boil at a temperature that's greater than 100 degrees. All right, so anyone wants to explain that? Why you think water, if you have, let's see, salt in it, it will take more than 100 degrees to actually cause it to start boiling. Anyone?
I have no idea.
No idea. Anyone has any idea? Let's think about it. We just did it with the kinetic theory of matter. What does adding impurities? When you add impurities, what is that in terms of particles? What are you doing in terms of particles?
Adding more particles.
All right, so you're adding more particles, right? And in terms of boiling, right? We just remember that boiling is changing from liquid to a gas, right? So if you're adding more particles, then that means you need more heat. So what's the purpose of needing more heat now?
In order for the in order for the excess particles to start move as fast as a body.
In order for the liquid to? Could you repeat that, please?
In order for the excess added particles to start move at the same rate as which none would be there.
All right, great. All right, so it's in order for the extra or the impurities to actually get to that point where it can actually break away to become that gas, right? So adding impurities is basic, especially if the impurities are solid. So if it's like salt in the water, right, you're going to need more energy to break away the salt particles, to change it to a liquid, and then from the liquid now to start changing it into a gas. So that's why it's impurities will cause boiling points to increase. The melting point of substances decreases with impurities. So why you think the melting now will decrease? So if you have salt water, why you think it will freeze at a higher temperature? So before it reaches 0 degrees, it will start to melt more than pure water. Because adding impurities to a pure substance increases the boiling point. Yes, anyone wants to try that one?
There are more particles in the substance, therefore increasing the forces of attraction.
All right, so increase the force of attraction. So what does that say about the heat that is required to freeze it? Well, to melt it, sorry.
Going to need more heat energy in order to break the attraction between the particles.
All right, okay. All right, so that's it for those right there. All right, so let's look at the type of mixtures. So the homogeneous mixtures are the mixtures have uniform particles throughout. So we're not able to distinguish the different types of particles that the mixtures are made up of, right? So just like if you use syrup and water, right? So when you mix the syrup and the water, you only get one color. So you're not seeing the syrup different from the water particles, right? So examples of those mixtures are like seawater, because the salt, sorry, will dissolve in the water. So you're not seeing a layer of sand and water, or the salt and the water, sorry. We have alloys, right? And alloys are mixtures of metals together. Milk, mayonnaise, alcohol, and water. Right? Heterogeneous mixtures that is not uniform throughout. They see different layers that it will make up. So sand and water. Right? So when you mix sand and water, you notice that the sand will settle at the bottom of the water, or oil and water, same thing, right? And sand and salt, same thing. You'll see the different particles present in your mixtures. All right, and a solution is formed when one substance called a solute dissolves another that's called a solvent. So solutions are homogeneous because they are dissolved within each other, so they are homogeneous mixtures. All right, so in this case, we're going to look at different solutions based on the state that they're in. So if we have a solid being a solute and the solvent is a liquid, right? Remember, the solvent is what is doing the dissolving, right? So example of this could be your salt and water, right? And if we have the solute being a solid and the solvent also being a solid, and this can be an alloy, right? Because two solids having a mixture is like an alloy, like brass or bronze, right? And then if the solute is a gas and the solvent is a liquid, example of this would be carbon dioxide in our sodas, right? So the carbon dioxide is your gas, and then our soda, liquid and liquid mixture like alcohol, And then gases and gases are like air, because we know the air is made up of different gases, right? And we obviously not able to see the different gases particles separate. All right, so let's look at distinguishing between suspensions and colloids and emulsions. All right, so with suspension, suspension is a type of mixture formed when a solute does not dissolve in a solvent, right? So what I normally use to define suspension is suspend means that you're hanging at the bottom. So you're hanging from somewhere, right? So the particles, so your solutes are actually that big that it's hanging at the bottom of your solvent. So like sand and water, the sand is actually at the bottom of the water, suspended there, right? So that's what a suspension is. Colloid is a mixture where the solute particles are bigger than those in a solution, but smaller than those in a suspension. So if the suspension particles are bigger, they are at the bottom. So for colloids, their particles are a little bit smaller than your suspension. So you're going to actually see it throughout the liquid itself. So it's not going to suspend at the bottom, but it actually is inside the liquid. But you still can distinguish between the liquid and the solute, right? So that's what a colloid is. So like glue or starch and water, right? So those are examples of our colloids. And then emulsions are a type of colloids where one liquid is finally dispersed in another liquid. So with emulsions, we only have emulsions when it's two liquid and liquid, right? So with mayonnaise or milk, so those things are created by mixing liquids together. So if you have two liquids that they dissolve, but you still have their particles visible, they are known as emulsions. Colloids are just general liquid or solid and liquid that you can see the different particles throughout the liquid or throughout the solution or the mixture, right? So let's look at the seal and fill it out. All right, so suspension, the particle size. What do you think will be here?
They are large.
Large. All right, so particles are clearly visible. So too large to pass through filter paper. All right. Passage of light. So what it means is if we shine light through a suspension, would it cause it to cause light to change its path, or does it reflect light or allow light to pass through freely?
No, it doesn't.
It doesn't allow that pass through.
All right. All right. We know those already. So variable depends on the size of the color and color of the particles. All right. So it varies for suspensions depending on the size of your particles that you're using. For colloids and emulsions, the light is dispersed by the colloid particles. Remember, with these particles, the particles are throughout the liquid, right? So those particles that you're seeing that's uniform throughout the liquid will cause the light to actually start spreading out, right? And there's a name for the spreading of the light when it passes through a colloid or a emulsion. Anyone knows that? That term?
Please. Repeat, please.
There's a term for the spreading of light when it passes through colloids. Anyone knows that term?
The scattering of light. I don't know.
No, there's an effect, a name that it's given to it.
The Tyndale effect.
The Tyndall effect. Right? So it's a
Then
Tyndall, the Tyndall effect. Let me write it in the chat so you can see how it's spelled. All right, so the Tyndall effect is that, oh, it's actually something that you should be introduced to before. So it's the effect where shining light onto a colloid will cause the light to actually spread. All right, so this that we have here, that light is dispersed by colloids, that effect is known as the Tyndall effect. Right? So please make a note of that because you probably will see it on a paper. All right, so sediments for suspensions, if the mixture is allowed to stand, then we know that the solute particles will settle at the bottom. So that's why it's called a suspension. For colloids and emulsions, the particles will not settle, they will just stand throughout the liquid. All right, so here we go. So the Tyndall effect is the effect of light scattering in many directions in a colloid dispersion. So this is a method in which scientists use to actually determine if a substance is a colloid or if it's a true solution. So if light passes through without any spreading, then it's a solution. If it passes and it's actually being spread, then it's a colloid. All right, so compounds are pure substances, right? Their composition is fixed. Composition fixed means that, let's look at NaCl, right? So it's just one Na that you need with one Cl to always make NaCl. So there is no deviation of that. So it doesn't matter if you have 20 Na and 20 Cl, it's just going to use one of that Na and one of that Cl to actually make the salt. All right, cannot be separated by physical means, so we cannot use salt, we cannot separate Na from Cl by using any of our separating techniques that we're going to actually look at soon. All right, so the physical properties are different from elements from each that they're made from. So the Na and Cl, their physical properties are different when it actually creates that salt. Right, and for mixtures, the composition varies. So it's just like mixing your juice. Sometimes you want to use this amount of sugar and this amount of water and this amount of fruits, and sometimes you can change it up, but you're still going to make the same mixture, right? Can be separated by physical means, which are or separating techniques that we're going to look at. The physical properties are the average of the substances in the mixtures. So the properties of mixtures are the combination of all the properties of their individual substances. All right, so let's look at this question. So we have three mixtures. We have their appearance when shaken, appearance when standing, presence of residue when filtered. And we need to see which one of these mixtures is a solution, is a colloid, or is a suspension. All right, so take like 2 minutes and look at it and see which one would you classify as being a solution, a colloid, and a suspension, or a suspension. All right, so let's go. All right, so are we finished classifying them? Anyone finish with this?
So,
All right, let's go through it together. All right, so what do you think mixture one would be? If it's white, if it's when shaken, it's white opaque. It's when standing, it's colorless, liquid is above, and a white solid below. And there's residue when it's filtered.
suspension.
A suspension. All right, so what in those description would cause it to be a suspension?
Liquid above, colorless liquid above white liquid.
All
Solid.
right,
That's it.
exactly. All right, so it's suspensions. We know that when it's standing or settled, we have the solid particles being suspended at bottom. All right, so mixture one would be a suspension. All right, so mixture two.
Colloid.
A colloid. All right,
Yeah.
why would it be a colloid?
It's white opaque and it doesn't change when it's left standing.
All right, so white opaque. All right, so that means we're still seeing some differentiation of particles in it. All right, there is no standing when it's settling, so that's not a suspension, so it has to be a colloid. And then mixture
Colloid.
three would be
Solution.
a solution. And why is it a solution?
Because it's
All right, so question one, classify each of the following mixtures as a suspension, solution, or a colloid. Sand and water.
suspension.
Suspension.
Yes, a suspension. All right, table salt and water.
Mixture.
Solution.
No, it's either suspension, solution, or colloid.
Solution.
It's a solution.
Solution.
Right? Chalk and water.
Suspension.
Suspension. Starch and water.
Colloid.
Colloid.
Colloid. Copper 2 sulfate and ethanol.
Solution.
Solution.
No, I have no idea.
All right, what do you know about copper 2 sulfate? What type of compound is this?
Solid.
No.
Oh, solution.
Compound. Solution.
Suspension.
All right, so copper 2 sulfate is an ionic compound, right? And
And
ethanol, we know, is a organic compound.
Suspension.
All right, so do they mix?
No, sir.
No, they don't, right? So therefore, we get
suspension.
a suspension.
Mm.
Right, so ionic and organic compounds don't mix, so we're not going to get a solution there.
Mommy. I just listen to all the stuff and then you can talk all the while.
All right, next. Oil and water can form an immiscible mixture or an emulsion. What is the difference between the two types of mixtures? So what's the difference between immiscible mixture or emulsion?
Immiscible is a mixture that do not mix.
And
Thing like
emulsion,
oil and water.
all right, and emulsion is
It mix.
mixed. All right, all right, we can go with that. So immiscible means that the liquids don't mix, right? And then emulsion would mean that they mix to an extent, but we still can see their particles. All right, how can the immiscible oil and water mixture be converted to an emulsion?
Mixing really fast.
Mixing it really fast. All right, so if we mix it fast, it
That makes
shows
sense.
the particles are in between. All right, so that, yes, that can work. Any other way you think it could work? And we also could heat it as well. So if we heat the water and the oil mixture to a specific temperature, it can actually form as an emulsion. Right? And the last question is name 3 different solvents.
Water.
Alright, so you all know the universal one, water,
Alcohol.
alcohol. Alright, one more.
Acids.
Acids. Alright, great. I was hoping someone would say like copper or zinc, right? Because those are solvents as well, right? Because they create an alloy, so they can act as solvents as well. All right, so since we've now went through our mixtures, impure and pure, let's look at how do we separate different mixtures, all right? And what makes it available for us to separate them and which technique is preferred. All right, so we know already that mixtures are impure substances. Many times it's needed to separate a mixture in order to obtain its pure compound, right? So some methods of separating mixtures are, so let's go. All right, so tell me the mixture separation techniques that you remember.
Filtration.
Filtration,
Crystallization.
crystallization. What's that?
Separating funnel.
Fractional
Separating
distillation.
funnel, fractional distillation.
Evaporation.
Could you repeat that?
Paper
Evaporation,
chromatography.
paper chromatography,
And simple distillation.
Separating funnel.
separating funnel,
Evaporation.
yeah, we thought evaporation.
I think
Alright, so
that's it.
simple distillation. Anybody know decantation?
No.
No.
Nope.
Is that also
Whether with that
filtration?
CHC not deal with that.
Decantation.
That
All right.
they use for
So
the
let's look at all that we just talked about there. So sublimation. Anyone said that?
Yes, Natalia.
Okay. Centrifugation and decantation. Filtration, which
oh, that's used
evaporation,
with
crystallization, simple distillation, separating funnel, solvent extraction, fractional distillation, and paper chromatography. All right, so let's go through each and see what's special about each. So sublimation. All right, so we know sublimation is changing from pure solid to gas. All right, so how can we? Why would we need to use a sublimation method to separate? All right, anybody remember the compound that was able to sublime from the previous slides? No, the
Iodine.
compound, not
The
iodine,
compound.
the compound. Which compound did we have that was able to sublime?
Ammonium chloride.
Ammonium chloride. Right? So let's say we have a mixture of ammonium chloride and table salt. Right? So we have ammonium chloride and table salt. We accidentally throw both crystals together, but we need back them separate. How could we get the ammonium chloride from our table salt? All right, so step one. What's the first thing that we would do?
See this solution.
Heat it. So we can just heat the mixture, right? So when we heat it, what's going to happen?
The ammonium chloride will sublime
All right.
into a gas, and the salt will remain
The salt will remain as what?
as a solid.
No, what state?
Solid.
Solid.
You sure?
liquid.
No, it's not. Not
Yeah.
really. All right. So when you heat, the salt will actually change to a liquid. All right. So it changes. It's going to melt. So it changes to a liquid, but your ammonium chloride will rise as a vapor. Right. So that's why there is that filter funnel at the top, so you can capture that vapor that will actually be released because the ammonium chloride will sublime. But the salt that remains will be in a liquid state because it's going to melt as well. Right, so in that case, we can actually just separate those two compounds and we can have the NaCl liquid state and we can just allow it to cool and it gets back to a solid, and then we have the ammonium chloride that's there. All we need to do is just really remove some heat from it and it comes back to being crystals as well. All right, so that's the reason. So that's important for sublimation because CXC normally likes to use sublimation and especially with salt and asks how would you separate a mixture of such. All right, so under the knowledge that ammonium chloride sublimes, then heating that mixture will causes it to sublime and we can get it as a vapor. Right, so that's why it's a sublimation method. So it actually is evaporation in a sense, right? But because it's only works well with compounds that are that sublimes, that's why it's a sublimation method. All right, so this one now is decantation. So decantation is not a very good way of separating mixtures, but it's something that we do regularly, especially in our everyday life or even sometimes in the lab. So decantation is where if we have no apparatus or instruments, and we need to separate, let's say, sand and water. Right? So we know the sand is at the bottom, the water is at the top, or we can use oil and water as well. We can just easily throw off the top mixture or the top liquid, right? And we leave back with our bottom ones, right? So it's basically, it's a simple method used to separate especially suspensions. So we have the solid part at the bottom that is settled, right? And we just throw off the liquid part at the top. It is not a very good method. And why you think it's not a good method of separating?
Some of the liquids
It's going to be fully separated.
Because it's never going to be fully separated, right? Because it's either we are going to allow some of the liquid to stay back, or we're going to actually throw until some of the solid actually comes out with the liquid, right? So it's not a very good separating technique. All right, and then based on this one, we know this is filtration, right? And filtration is used to separate what type of mixtures?
Suspension.
Suspensions, yes. So it's used to separate suspensions, and please note that the solvent and solute, it has to be a solid and a liquid, right? So to create the mixture, it has to be a solid and a liquid. So we can't use filtration to separate oil and water because there is no solid in that, right? So it has to be that one of those solvent or solute is a solid that was not able to dissolve. So we can actually get the liquid part and the solid part remains, right? And we know that the liquid that flows through the filter paper is called the filtrate, and what it remains in your filter paper is called the residue. All right, so this one now is crystallization, right? So crystallization is the same as evaporation, right? But in this case, we want the solid part. So let's say we have salt and water, right? So we have salt water, and we need the salt from the water, right? So after we mix the salt water, we realize that we want back the crystals from the salt from that mixture, right? So we heat it so the water can actually evaporate, right? And also it will evaporate with some of the solids. So at the top of the evaporating basin, we normally have a glass container, right, to cover it, right? And then after a while, we're left back with the salt at the bottom of the basin, and then we cool it to get back our crystals, right? And then this one, which one is this? Fractional or simple?
Simple.
All right, so simple. All right, so when do we use fraction and when do we use simple? Yes, anyone?
Fractional simple distillation, I think, is used when there is a large difference in the boiling points of the liquids or substances you're using. But fractional distillation is when the boiling points are close together.
Very good. All right, so simple distillation is when the boiling point of your liquids are far apart. So that means one can actually evaporate quickly than the other one. So, right, so that's where we use simple distillation. All right. What's the purpose of the water going in and water going out of the condenser?
Cool down something.
Cool down. So what exactly is it cooling down?
I don't know. It's cooling down the vapor so it can turn to water quickly enough to go down into the, what's that?
Exactly. Right? So when the first liquid that has the lowest boiling point, when it vaporizes and it's going through the condenser, we need the liquid form of it. Right? So therefore we use water to cool it down so it can actually convert back itself to a liquid form to be collected there. So that's the purpose of the water going in and out. So we consistently have the water going in and out so we get a cool water to cool down the gas so we can actually condense. Alright. Alright, there those porcelain chips at the bottom of your flask or the boiling tube, the boiling flask. The purpose of those. Anyone know the purpose? Anyone?
Sir, we don't know what those are.
Okay. Alright, so the chips, right, they are there to actually cause boiling to be smooth, right? So let's look at what happened when you have water and oil in a pot and it's heated, right? The boiling that will occur will be a random vigorous boiling, right? We don't want that when we're doing simple distillation or fractional distillation. So we use these chips as buffers basically to actually cause the substance or the solution there, the mixture, to boil at a constant rate, right? So it don't actually get violent over a period of time. So it consistently boils at this speed, right? So that's the purpose of those chips. All right, everybody got it?
Yeah.
Okay. All right, and then this one would be our separating funnel, right? And we know we use it to separate what type of mixtures.
Immiscible mixture.
All right, immiscible mixtures. All right, so in this case, we can just pour off the one that is the more dense. All right, so the one at the bottom, we just pour it off. So we have two different layers. All right, so it's solvent extraction is not one that's required. So we can skip over this one. All right, and then this one now is our fractional distillation. We use it because the different components of your mixtures have very close boiling points, right? So the column, the fractional column is there to separate the vapors as they enter based on their boiling point, right? So that's the only difference. It has its fractional column to separate the vapors. All right, we know this one is our paper chromatography, and we use this one to separate
Dyes in ink.
dyes in ink,
Dyes. Yeah.
ink dyes. Right, so it
Something.
separates our inks, colors in our inks, right? So it's basically pigments. So it separates pigments because each color has its own basically density, right? And it's able to dissolve in the specific solvent at a different rate, right? So the reason why when you put your food dye on your paper chromatography paper and you put it in water, The reason why you see the different colors, because each of those colors have its own solubility in water. So this method is based on the different color solubility in the specific solvent that you're using, right? So that means the solvent that you choose have to be one that your pigment is able to dissolve in, right? So it's important to choose a solvent that your pigments are able to dissolve in. So we normally use water or we use ethanol or alcohol, right? So based on their solubility, they will move accordingly. So they separate based on their colors. Right, and we know we have our retention factor, right, which basically tells us how easily each pigment will actually move throughout our solvent. So the solvent will rise to the extreme, to the maximum point, and then below those, the solvent line, you'd have your different pigment colors, right? So the color that is closest to it would actually have the lowest pigment, the lowest retention factor, right, compared to the one that's further below. All right, so this table here will gives a specific layout of your different type of mixtures and the different methods that you'd use to separate those types of mixtures, which we did before. All right, so we're going to, all right, so let's look at this one now. State the method you use to separate the following substances: calcium carbonate from table salt. How do you think would separate calcium carbonate from table salt? Anyone?
Crystallization?
Crystallization? Do you think crystallization would work for this one? Because what's unique about both of those compounds? They're of the same type, right? Calcium carbonate and table salt, sodium chloride, they are both ionic compounds, right? So if we heat them, they're both going to actually just melt and evaporate at the same. So how could we get what's different, even though they're they are same type of ionic compounds? What's different if we are actually supposed to mix it in water?
One dissolves and one doesn't.
No, they're both ionic. They both will dissolve. But their boiling point in regards to water will be slightly different, right? So therefore we can use our distillation to actually separate it, right? And then we can do crystallization. So you have to distill it first and then do crystallization after. All right? All right, B, iodine from sodium chloride. How do you separate that one? Anyone? Uh, what's unique about iodine again?
Is that
Does
the
it
one that
sublime?
sublimes?
Exactly. So it's sublime, so therefore we can use sublimation to actually separate iodine and sodium chloride. All right. All right. Table salt from seawater. So we need to get the salt from the seawater.
Crystallization.
Crystallization
Distillation.
Yes.
or distillation.
Distillation.
Yes. All right. Sugar from sugar solution. So that means we have sugar and water and we need to get back the sugar from it.
Crystallization.
Crystallization, yes. All right, next, pure water from sewage water.
Distillation, one of them.
Yeah, distillation.
Depending on
Right,
the boiling point.
so it's simple distillation
Simple
will do.
distillation.
Okay. And then next, ethanol from beer. So do we get ethanol back from beer?
Distillation.
Distillation, yes. All right, last one, yellow dye from the durian ice cream.
Chromatography.
Exactly. So once you hear dye, it's chromatography. Right? All right, so that's it for your separating techniques. All right, and that's it for pure and impure substances. Yes, that's it. All right, so I will stop here for today and we'll resume tomorrow with not tomorrow, Thursday, sorry, Friday. I don't remember the time. So resume with continuation of the syllabus, and from as of next class, after each session, we'll actually try to do some questions, multiple choice questions based on those topics that we did. All right, so we're going to look at the periodic trends in your periodic table and also structural bonding, and hopefully we can do some part of moles as well. All right, so thank you guys for watching today and attending today, and see you guys next time.